All right, guys, welcome to chemistry lesson 8.05 on single displacement reactions. So what we're talking about today are reactions where we're going to displace either the anion or the cation. And we said previously that we can look at these as our general formula as AX plus B, giving us BX plus A. And what I've done here is I have replaced cation. So I swapped my cation. The other way we said we could express these was we could say you take AX plus Y, and that gives you AY plus X. And what we're doing here is we're swapping our anions. The way that you can tell is, remember originally when we talked about, when we did our overview, we said that A and B are metals. So this is going to be a metal. So if we're reacting a compound with a metal, we're going to swap the cations. We're going to end up with BX plus A. Y and X and Y represent nonmetals. So if we react a compound with a nonmetal, we're going with an anion swap. And we're going to look at an example of each of these. All right, so for our first example, and for the demonstration today, whoops, get my white out, DEM. For our demonstration, we reacted zinc with tin 4-chloride and if you haven't seen this in class, if you're watching this at home, please pause the video now and go to the YouTube link that has the video for this reaction. Okay, welcome back. And what you saw was that we swapped and we produced a solid tin plus zinc chloride. Zinc chloride is one word. I kind of made a big space there, so do that. So what does this reaction look like? How do we write it out? How do we balance it? And then the other thing we want to talk about is what gets oxidized and what gets reduced. All right, so we always, if we're starting out with the word equation, we always want to write our symbols, our ions with our charges. So we're looking at zinc here. Zinc's by itself, it's an element. So we're going to put Zn, and I'm writing this up above, right? Because this isn't going to be my reaction. And I put the neutral sign, because remember, when something's in element form, it's neutral. Then I've got tin that's +4, so I go Sn +4. And this chloride ion has a -1 charge. On the right side for my products, I created tin in its elemental form. So I have Sn, and that's got the 0 because it's neutral. And then I have zinc, Zn, that's going to be +2, and chloride is -1. So when I go to write my formulas, and always write the formulas first, balance second, I'm going to have Zn plus, I have a +4 charge here, a -1 here, so I need SnCl4. I need 4 of these to get that +4 charge. And then I'm going to have tin, and that's going to be neutral. Be careful because I almost just put a sign on my equation, and that makes your equation wrong. We don't put symbol charge or charge symbols on equations. My zinc is +2, my chloride's -1, so I need ZnCl2. To balance, I need, I have 2 chlorine here, I have 4 here, so I need a 2 here. That gives me 4 chlorine. I have 2 zinc, so I need a 2 out here, and I have 1 tin and 1 tin. So there's my balanced equation. Okay, now I need to look at who gets oxidized and who gets reduced. when you're looking for oxidation reduction, you have to look at what's on the left side of the equation versus on the right side of the equation. Now, I can ignore chloride because look at chloride. It's -1 over here. It's -1 over here. Did chloride change at all? It didn't. Over here, my zinc is neutral. Over here, my zinc is +2. Did my zinc change? Yes. If I look at zinc, I go from Zn neutral to Zn +2. And if I look at my tin, on the left, I have tin +4, and I go to, on the right, neutral tin. So when I look at zinc, I see that zinc has 30 protons. And when it's neutral, I'm going to have the same number of protons and electrons. So I have 30 protons, I have 30 electrons. But I go to zinc that has a +2 charge. Well, let's work out our protons and electrons first. So I'll do a zinc, and then I'll do the elements, then I'll do the charges. So now we've got tin, and tin has 50 protons, and when it's neutral, it's going to have 50 electrons. Okay, so what about my ions? Now I have ones that have charges. Zinc is still going to have 30 protons. We know the protons never change. Here I have a +30 charge. Here I have a -30 charge. So this ends up being 0. If I want a net charge of +2, whatever I have here for +30 plus this negative charge has to equal 2. So that means I have to have 28 electrons to have a -28 charge. That gives me +2. Over here for tin +4, I'm still going to have 50 protons, but I need to have an overall +4 charge. So that means that I need to have 46 electrons to give me that -46. Okay, when I analyze this, I went from 30 electrons to 28 electrons. I lost electrons. Zinc lost electrons. Tin goes from 46 to 50. Tin gained electrons. And if you remember, oil rig, oxidize is lose, reduce is gain. That means that zinc was oxidized. And that means that tin was reduced. This is a little blurry. I'm going to see if I can refocus. It's about as good as we're going to get. All right, and so what we were looking at there was this. That's when we swap cations. Let's look at a second example where we're going to swap our anions. So sample problem number 2. Let's take potassium bromide. Potassium bromide plus chlorine. So on the right side, that could give me potassium, it could give me chlorine bromine, or it could give me potassium chloride. Hopefully you understand that this is a non-metal, so I'm going to have to swap these. And I'm going to end up with potassium chloride plus, I'm running out of room, plus bromine. I'm just going to write that in its element form because I'm running out of space. Okay, potassium is +1, bromide is -1 when it's in a compound. When chlorine is by itself, it's diatomic and it's neutral. Over here, potassium is +1, chloride is -1, and we have Br2, which is neutral because it's diatomic. So when I write this formula, I have KBr, because of my +1, -1, plus Cl2 is going to give me KCl plus Br2. The balance, I need a 2 here, and I need a 2 here. So now the question is, who gets oxidized and who gets reduced? Do I have to worry about potassium? Potassium's +1 here, +1 here. It doesn't change. There is no change in the charge for potassium. But if I look at bromine, or bromide, I should say, I go from Br-1 to Br, it is Br2, but that's okay because it's neutral. And for chlorine, I have neutral chlorine, Cl2 to Cl-1. All right, let's look at my neutrals first. So for bromine, bromine has 35 protons. So this is going to have 35 electrons. And chlorine has 17 protons, and it's neutral, so I'm going to have 17 electrons. So to have a -1 charge, to go from -1 to 0, that -1 charge indicates that I have 1 extra electron. I still have 35 protons, but I have an extra electron here. So I have to have 36 electrons. That's a +35 minus 36. That gives me that net charge of -1. Over here, I still have 17 protons, but I have to have 1 extra electron because I have a -1 charge. So this has to have 18 electrons. So if we look at bromine, I went from 36 electrons to 35. I lost electrons. Bromine was oxidized. If I look at chlorine, I went from 17 electrons to 18 electrons. I gained an electron here. Oil rig oxidizes, lose, reduces, gain. So chlorine was reduced. And that is an example of swapping our anions, which was up here. So what are our takeaways? In a single displacement reaction, we're either swapping the cation, metal for a metal, or the anions, non-metal for a non-metal. Go through the same procedure for writing out your formulas first and then balance. Once that's done, you can look at what changes. So it's always going to be what's being swapped is going to be metals will be oxidized, reduced, or the non-metals. Analyze your protons and electrons to figure out who gained and who lost, and then assign your oxidized and reduced labels. It's always easier to figure out who gained and lost and then assign this. By the way, as an aside, because we talk about reduction and oxidation, these are also called redox reactions for reduced oxidized. So if anybody asks you about a redox reaction, you've already done it. All right, that's all for now. Thanks for watching.